In this brief video of just over 30 minutes, I will be discussing about the evolution of cellular mobile telecommunication systems from the first generation network to the ongoing fifth generation network and upcoming or forthcoming sixth generation networks. So we'll be talking about some of the features, limitations and some fundamental technologies in all of these generations of telecommunication systems. Myself, I am Ahmed Kamal Hassan, and my area of work deals with electronics and communications. Before moving towards the first generation networks, let us look into the timeline and how these generations are stacked together. So over here you can observe that the second generation was basically in 1991, and anything which was prior to 1991 was the first generation network 1G, right? And after 10 years we got 3G, approximately 10 years we got 4G. We are presently at the verge of implementation for 5G, and then we would have a time frame forecasted for 6G networks, right? So this timeline doesn't mean that between 1991 and 2001 there was no change in the network. In fact, there was considerable change, but that change were more related to the upgradation rather than infrastructural change, right? So for example, in 1991 you had 2G, and in between you had 2.5G, also called GPRS, and then you got 3G and so on. So the major change or the infrastructural change is after 10 years. So let us look into the features of the first generation network. First experience of wireless telephone communication was introduced in the first generation networks. So it was launched under several brand names, including Advanced Mobile Phone Systems in USA in 1983. We also had a protocol for Europe and for Japan. So we had bulky cell phones, but the main thing was it was allowing us to communicate by means of wireless channel, right? And then it was built on analog signals. It was using frequency division multiple access (FDMA). This is very similar to your FM broadcast receiver that you have in your vehicles. That is, different channels are allocated different frequency bands, right? So if you have tuned to 88 megahertz, so at all times the 88 megahertz station is basically transmitting the intended data. You can call freely within a network. That is, if you are in USA, then you would be using amps, and within amps you can have handovers, but not beyond it, right? So you need the same infrastructure to do the handover. And also the speed limit was quite low, but it was at least good enough for voice communication. It was basically 2.4 kilobits per second, right? So since it was a seminal technology, there were several limitations, including the big size and the weight of the device. So it was not very handy. Moreover, battery drainage issues were there because there were a lot of components which were not based on the recent semiconductor devices. So they were consuming a lot of power. And then you had low SNR, that is signal to noise ratio. So you had a bad voice quality and poor encryption and security. So why it had poor encryption and security? Because each user was given a specific frequency band. So there was a possibility of eavesdropping, so somebody else can tap on a given channel, and hence there was a concern of security. And last but not the least, there were severe issues in terms of call drops when there was mobility. So that is, there was a bad performance in terms of handover, or also called as handoff. So why it was like that? Assuming this is one base transceiver station which is transmitting signal to a cell phone, which we have represented over here as a mobile station. So if the mobile station is moving from this location to this location, so the quality of signal from the original base station, the old base station, will be dropping, right? At the same time, the SNR for the second base station will be increasing, right? So we need some algorithms by means of which the mobile station can be connected with either of the two base stations. And if the algorithm is not efficient, we would have a lot of call drops, specifically in this region. So the issues of call drop were actually later on fixed in next generation networks. So citing all these limitations, the second generation networks emerged. Second generation networks also goes by the name of Global System for Mobile Communication, that is GSM, and it was launched in 1991 in Finland. Note that a Finnish company, that is Nokia, which has basically given us a lot of communication infrastructure as well as cell phones, right? And most of us would have seen this cell phone, that is Nokia 3310. So the major difference between first generation and second generation was the digital signals. So in the second generation we had digital signals, and for that we had QPSK, right? That is in phase, quadrature phase, and then you would have some symbols. So any given time instant you could send a symbol of 2 bits rather than 1 bit, and that was a major advantage. So it gave a rise to data rate, as we will see next. Also in 2G, the short message services were enabled, and moreover digital encryption was also enforced. So we had more security and encryption in 2G networks as compared to the 1G network. Furthermore, it was based on time division multiple access. That is, rather than frequencies, now the time was divided, right? So each user was given a specific time in which it can communicate, and moreover, the uplink and downlink can also communicate based on different time slots on a same frequency channel. An important feature over here is the concept of cellular technology, and for that, if you look into this figure, so over here we have different cells. Say this is our first frequency, which is f1, right? So the neighboring frequencies are over here shown. Say this is f2, f3 and f4, right? So all the neighboring cells have different frequency bands, right? So they would not interfere with this given cell, but at the same time you have the capability of reintroducing this f1 over here, right? So the signals from this base station will have very minimal effect on this base station. Note that this is a very simple structure based on hexagrid, but importantly the intra-channel interference has been mitigated to good extent. 2G networks provide better quality. This is simply because in digital signals now we have ones and zeros, and the threshold detection is quite easy as compared to analog signals, right? Also, we have reliable horizontal handoff, right? Handoff is handover, as I mentioned previously. And what do we mean by horizontal handoff? Horizontal handoff is simply the handoff between the same technologies. That is, if you are using a cellular network and again you're moving towards a cellular network, so that kind of a handoff is basically horizontal handoff. But you also have a vertical handoff, and that vertical handoff is simply if you are in a cellular network but you are streaming some data, but at the same time you also have a broadband Wi-Fi availability in your given location. So you could have a handoff between base station and the Wi-Fi or the broadband technology. So in 2G, the handoff is more reliable. You have certain algorithms, including the Hu margin. That is, if again the mobile station is moving from this location to this location, originally it was connected to an old base station, and now it would be connected to a new base station. But as it is moving from this point to this point, so over here or over here, the handoff has not taken place. So if the threshold is met, and that threshold level is based on this Hu margin, right? Until there the difference between the two signals is considerable, so there will be no handover. And once there is a handoff, then this mobile station will be connected to the new base transceiver station. So such kind of algorithms give us a more reliable handoff, and the possibility of call drop during handoff is minimized. And importantly, we have a speed improvement to 64 kilobits per second from 2.4 kilobits per second of 1G network. Now, talking about the limitations of 2G network, receiver sensitivity in time division multiplexing systems actually is an issue. Why this is an issue? Because, for example, if we are going to transmit 00011011, so we could have this signal followed by 01, which could have a different amplitude, 10, which has the same amplitude, but now the phase is different, right? So over here the phase has changed, and again in 11 we have the phase change as well as the amplitude change, that is. So there are different levels by means of which we are transmitting a signal in time domain, right? So this is a time domain plot. You could also have an constellation diagram, which is simply IQ, right? So therefore, detecting all these different kind of structures is an issue at the receiver side. Also, it is bad for video data because 64 kilobits per second is not sufficient for video signals, right? So we could access the audio data but not the video data, right, or the multimedia. And hence there was an upgradation somewhere over here that is referred as 2.5G, and this is General Packet Radio Service, GPRS, and this was a packet based technology. And this is, as I mentioned, in between 2G and 3G. We had multimedia messages, internet browsing, so you could call different people at the same time. Importantly, speed improved from 64 kilobits per second to 144 kilobits per second, right? And in short, if you have a 3 minute of MP3 file, so this would take 6 to 9 minutes to download, right? So this brings us to the next generation, which is third generation 3G. It was launched in around 2001, and its features include integrated high quality audio, video and data. So this enabled from a group audio call in 2.5G to a video conference in 3G. Also, you could have a mobile TV on your cell phone and you could easily access the internet. This is iPhone 3, and over here you can see the coverage which is 3G, right? And this enabled broadband and IP technology. Code division multiple access was used, that is, different users were accessing or communicating with the base station at all times and for all given spectrum, but they were divided in terms of different codes or orthogonal codes. This also ensured better encryption, and we again had horizontal handoff but not vertical. The speed improved to 2 megabits per second from 144 kilobits per second in 2.5G. So you could download 3 minutes of same MP3 file at an average time of less than 1 minute as compared to 6 to 9 minutes in 2.5G. But of course, the 3G had some limitations. First and foremost, more number of base stations required as compared to 2G network. So why do we need more base stations? This is because the same constellation diagram, that is IQ, now it has more symbols. And if it has more symbols, the receiver would find it difficult to distinguish between the symbols, right? Between this symbol and this symbol. So the receiver will become more and more complicated, and hence you would need a shorter distance between a base station and a mobile station. So you would need more densification or more base stations. So this is going to increase The capital and operational expenditure. Capital expenditure is simply that you're going to install new sites, new base transceiver stations, and the cost for that. And the operational expenditure is the cost of maintaining those sites, right? Operation and maintenance of those sites. So also at the time in 2001, the 3G phones were quite expensive as compared to the per capita income, and it needed high bandwidth requirements, high quality video streaming with high latency, right? So by this what we mean is, first, what is latency? Latency is nothing but a delay, right? So if you are requesting a service, how fast can you get that service? So this will be dependent on the latency, right? So if you are downloading a high quality video, so there will be some delays. That is, if you click on a video, it will be buffering for a long time, right, before the video actually plays. So based on these shortcomings, in 2010 we had the fourth generation. So we had long-term evolution LTE, and its another version or advanced version which is called LTE advanced, right? And it was first all packet switched technology. Note that the long-term evolution, this LTE, conventional LTE is not 4G. It is often referred as 3.9G because it was not exactly following the protocols of 4G. But LTE advanced is actually the prime example of 4G. So this is iPhone 7, which can be used to access 4G technology. And the main theme of 4G is basically multimedia, anytime, anywhere, right? So you have mobile TV, online gaming, cloud computing. So all of these features are actually enabled in the fourth generation, right? So anything, anywhere. So it is using orthogonal frequency division multiple access for the downlink and single carrier frequency division multiple access for the uplink, right? So it is operating at two different bands in the downlink and uplink. So it is a half duplex system. It is not using a simple a given spectrum for both uplink and downlink. Note that downlink is the communication between base station to the user. If base station is transmitting a data to a user, so that is downlink. But if you are uploading a data to the network, right, so uploading a data from mobile station to the network is called uplink, right? So 4G was first of its kind in terms of horizontal and vertical handoff, right? So it is able to not only hand over between different base stations but also across the technologies, that is 4G to a broadband Wi-Fi router. This cell phone has an assist enabled feature which would use both the broadband as well as the cellular technology together, and it would download a big file if needed, right? So there was a 100-fold increase from 2 megabits per second to 200 megabits per second in 4G. And this means that if you have a 60 minutes of HD video, right, so this would take roughly 6 minutes to download, right? In 2.5G, 3 minutes of audio was taking roughly 6 minutes. Now 60 minutes of HD video file would be taking 6 minutes, right? So what are the limitations of 4G? So why do we need all these technologies? The first and foremost is the emerging Internet of Things, right? Everything is connected in Internet of Things. At least it is supposed to be like that, and hence there is a massive connectivity. So this 4G, it gives us a good data rate, but it cannot enable a lot of devices to be connected to a network, right? So this has this limitation that not a lot of devices can be connected to a 4G network, and we cannot accommodate massive antennas in base station. While 4G has multiple antennas, but it does not have massive antenna structure. The use of massive antenna structure, as we see in the 5G setup, that it gives us some relaxations in terms of channel state information. We could direct beams towards the given user more reliably, right? And the communication is actually more green. Also, the delay or the latency for augmented reality or virtual reality games and healthcare applications is quite high. So we cannot rely for healthcare services based on the current 4G network. So based on these limitations, we have the 5G networks, and we are presently in 2020, and the 5G networks is actually being launched since 2019. It is not fully launched everywhere. Actually, it's very sparse at the time being. It has been launched in some of the places in China, Britain, but not elsewhere. The first cell phone technology that was basically launched is from Samsung. This is Samsung Galaxy S10. So this enables the access of 5G network, right? This was launched in 2019. So it was first of its kind at the time. The important features include huge number of devices to be interconnected to the network. So that is 10 raised to power 5 devices per kilometer square. So this is a big number, right? So if you have this big numbers, so you are not actually relying on your personal communication, that is base station, to the cell phone, but you also have other kind of communication. For example, vehicles to X, right? Vehicles to infrastructure, vehicles to vehicles, vehicles to pedestrian networks, right? Body area networks, different kind of sensors which are relaying information, washing machines, refrigerators, they are connected, right? So different and multiple technologies are basically connected under the theme of Internet of Things. Hence many new applications beyond personal communications. Now what are the requirements of a 5G network? Definitely you need high throughput, that is 60 minutes of HD, which took around 6 minutes previously. Now it should take around 6 seconds to download, right? 60 minutes of HD video in 6 seconds. Importantly, the delay or the latency, that is a round trip delay, that is from a user to a network, say to another user and then back towards the original user. So that is basically 1 millisecond, and this enables the tactile internet. And what is that? So previously we are visualizing the information in terms of HD video and listening to it. So we are using two receptors. So in tactile internet we could have more sensory receptors that are also enabled. For example, in this setup, I have taken this picture from Kirkinfo, and over here you can see there is a VR gear that the batsman is wearing. So on the other hand, you can have also a bowler which is facing also a VR gear. So you could have an actual player-to-player match based on virtual reality, and this is a very beneficial feature specifically, and God forbid if the pandemic situation continues and worsens. So such kind of applications are basically enabled by means of 5G technology. And we also have energy efficiency, since the beamforming or the waveforms are actually directed towards a specific users and it is making small lobes, right? The key technologies in 5G include extreme densification and offloading. So the network is very dense and we have small cells and macro base stations giving service simultaneously, and the distance between the mobile user, that is the cell phone, and the access point, which is the base station, small or big, right? So that is actually quite small, right? The average distance is quite small, and it is also giving us an option of offloading. And for that offloading, previously we were more concerned in conventional systems uh, that if there are different users which are communicating with each other, so we had control of their data as well as the control or telemetry. But right now, if the two users are communicating within a base station, so they can directly communicate the data by means of device to device communication, but the network is going to basically control them and charge them if needed be. Another important technology is massive MIMO, and for that you have a large antenna array at the base station, right? Whereas you could have one or few antennas at the mobile stations. So a number of antennas. So if there are a number of antennas at the base station, there is a phenomena which is called channel hardening, and based on channel hardening, the mobile station does not need to acquire the channel state information, right? So it is quite beneficial, and you could use low complexity algorithms to get the desired service. More details for such are given over here, right? And next is millimeter wave spectrum. So millimeter wave spectrum is around 30 gigahertz and up to 300 gigahertz. So this spectrum is actually not used presently in communication systems, and hence this enables a big bandwidth or a big spectrum that can be utilized, and this is one of the key advantage or the key technologies of the 5G networks. But of course this has a lot of limitations, because you can see this is a non-linear behavior of the frequency band with respect to attenuation dB per decibels per kilometer, right? Even though it is non-linear, but you could see that you have certain peaks of attenuation. Moreover, the pattern is actually increasing as the frequency increases, right? So you have more attenuation. So hence we have two different topologies. One is for the line of sight base station directly in line of sight with the mobile station, and then we have non-line of sight. So you do not have a line of sight with an access point, so you have a non-line of sight. So we have to consider both line of sight and non-line of sight communication in millimeter wave spectrum. So while the millimeter wave is from 30 gigahertz to 300 gigahertz, the 5G technology is also operating at around sub 6 gigahertz bandwidth, specifically at around 3.5 gigahertz, which has not been used to a greater extent. So while there is advantage, but at the same time it is challenging. So what are the limitations? Huge capital and operational expenditure. So this is one of the bottlenecks. Because of huge densification of network, you would need a lot of capital expenditure. You need to install a lot of access points, and you need to maintain and do operational expenditures, that is operation and maintenance on those installations. So we have to invest a lot in terms of infrastructure. Since most of the things are interconnected, that includes vehicles, so the security and encryption becomes even more important, and it is yet to be fully regulated. Moreover, it is yet to achieve the promise, right? So all the technologies that we have, they don't give us this kind of throughput, right? That is 1000 fold from the 4G network. But note that we are over here, and as we move forward, we will have more and more advancements, and eventually and hopefully we will achieve the promise set forth by the regulators. This is in accordance with 3.9G, that is LTE not achieving the 4G promise, but at the same time LTE advanced achieved the 4G promise, right? So eventually and hopefully it will achieve it, right? The big question, have we covered most of the things? So why are we moving towards the sixth generation networks? And the reason for that sixth generation network, first and foremost, the research started in 2019 on 6G. And why do we have this debate over here of the sixth generation network? This is because the 5G wireless networks offer substantial improvement over 4G, yet demands a full connectivity, that is connection of all devices on the network, is still lagging in 5G. So we need better infrastructure to tackle the industrial revolution 4.0, right? So in this paper, some of the key proposals related to sixth generation networks are proposed, right? And those includes interconnection of 10 power 7 devices per kilometer square in 6G as compared to 10 raised to power 5 devices per kilometer square in 5G, and peak data rate of 1 terabits per second in 6G as compared to 1 gigabits per second in 5G. That is 1000 fold increase in data rate. and then unmanned mobility sport of 1000 km per hour in 6G as compared to 500 km per hour in 5G. But note that this is unmanned mobility, not manned mobility. For example, for the drones and autonomous aircrafts. Furthermore, reliability of connection and remote operation, that is the reliability has increased 99.99999% in 6G as compared to 99.999% in 5G. Suppose there is a surgery going on in a remote location where you only have haptics and robotic arms, so you need to make sure that you do not lose connection while performing that kind of a surgery, right? And moreover, the VR virtual reality games also need high reliability, right? So the healthcare systems and vehicle networks, drone networks, right? So all these networks need an assurity in terms of reliability, right? Lastly, the latency or the delay is proposed to be 100 microseconds in this work in 6G as compared to 1 millisecond in 5G. So I'm not sure by this latency what it would mean, but maybe this visual can assist us. Right. So we would have metrics coming to reality hopefully in the sixth generation networks. So in this video we have covered evolution from 1G to 6G. For architectures of the implemented technologies, follow the playlist in the end screen of this video. Thank you.